Swayam Prabha. Digital India. Educated India.
So, in the last lecture we were discussing about virtual memory. We talked about demand paging, paging a load into physical memory on demand. We talked about the need for replacing a page replacement. So, we shall be continuing with that discussion today. Okay. So, this is the third lecture of the module. So, under demand paging, the first thing that we shall be talking today is something called locality of reference. Now, understand one thing, we are saying that we are having a page table to speed up the process, we are having a TLB. We said that the pages that are accessed recently are loaded into TLB, but why? What is the justification for that? So, our intuitive justification is the pages that are accessed now will again be accessed in the near future, but what is the basis of that? So, that is something which comes from this phrase locality of reference. Let us try to understand what it is. Locality of reference essentially is a property of computer programs. It is a property of typical computer programs. Of course, you can write a program where this locality of reference will not be visible, but for most programs that we run, this property of locality of reference holds. What it says is that it is the tendency of computer programs to access data or instructions that are near each other in memory. Basically what it means, if this is your, let us say, logical address space, and at any point in time suppose you are accessing some memory location here. So, what the property of locality of reference says is that the nearby memory locations, it is extremely likely that the nearby memory locations will also be accessed in the near future. So, it makes sense if we can keep these nearby memory locations in memory, so that in the future when these accesses come, they will always be present. You will not have to load those pages from secondary memory into physical memory. Now, broadly speaking, there are two types of locality you can think of. These are called temporal locality and spatial locality. We shall be discussing this. Temporal locality, temporal means time, locality in time. Suppose I am accessing a memory location X, within a certain time in the future we will again be accessing memory location X, that the same memory location or the same data will be accessed repeatedly in the near future. This property is called temporal locality. And the second one is spatial locality. Spatial means space, that if I access memory location X, then X plus 1, X plus 2, X plus 3, the nearby memory location, they are also likely to be accessed in the near future. Okay. These are the two kinds of localities we can define, but let us understand why we are talking about temporal and spatial locality, why they occur. Okay. Let us try to justify this. First, we talk about temporal locality. Let us understand what are the scenarios which can cause temporal locality to show up in a computer program. Now, as I said, what is temporal locality? Temporal locality is a property of computer programs, or you can say tendency of computer programs to access the same data or instruction, which means same memory location, repeatedly or multiple times within a short period of time. Okay. And there are several reasons why this temporal locality may show up in a program. Most important is loops and iterations. In a typical program, we use loops, right? Many a time we use some data structure like arrays, where we access the data elements in the array one by one. These are repetitive operations. Now, when you are doing these things in a loop, the same piece of code will be executing repeatedly one after the other. So, the memory location that was accessed in the first iteration will again be accessed in the second iteration, again in the third iteration. So, because most of the time a program spends its time in the loops, these are the instructions where special locality will show up. Some set of instructions will be executed repeatedly because they are part of a loop. Suppose these are the instructions and there is a loop. So, these instructions will be repeatedly executed. Okay. Secondly, suppose in a program there is some function or some procedure call which is invoked repeatedly multiple times. There is some function which you are calling multiple times from a program. Now, inside the function, let us say this is your function, let us say f. Inside the function there are several instructions. So, when you call the function several times, those instructions inside f, they will be executed repeatedly multiple times. That is what causes temporal locality with respect to these instructions. Okay. So, first is the presence of iterations, second is the presence of function calls which are invoked multiple times. Of course, third one is a general property. Say this depends on the way we organize the data in the form of a linked list or in form of array and so on. It says when some data is accessed, it is likely that it will be accessed again in the near future. You think of operations like matrix multiplication or things like that. So, the same rows and same columns of the matrix will be accessed over and over again in a loop. So, all these things contribute to the property of the program that shows up as temporal locality. Okay. So, essentially what I am saying is that in temporal locality, you have a program, you have several instructions. Let us say this is memory location x, generally let us call it x plus 1, x plus 2, x plus 3 and so on. So, due to some reason you are executing these instructions repeatedly. So, they are in a loop or they are part of a function or procedure which you are calling multiple times. So, what will happen? X will be accessed multiple times. Similarly, x plus 1 will be accessed multiple times, x plus 2 will be accessed multiple times. This is called temporal locality. Similarly, suppose you have declared some data, let us say you have declared an array, let us say x100. So, in memory the data items will be stored one after the other. Say first one will be x0, then x1, x2 and so on. Now, when you write a program which is doing some manipulation on these arrays, possibly this manipulation is inside a loop. So, the same set of data may be accessed multiple times. So, in the first case I am talking about accessing of instructions, in the second case I am talking about accessing of data. In both cases temporal locality may show up. Of course, it depends on the algorithm that whether you are actually using the array kind of data, you are accessing them repeatedly, okay, then temporal locality can show up. Okay. Secondly, let us come to spatial locality, which I have said this is again a property or tendency of programs where you are trying to access data or instructions that are stored close to each other. For temporal locality, we are saying that the same location is used multiple times, but here we are saying that the nearby locations will be accessed in the near future. Okay. Now, here again similar kind of properties in the program may result in spatial locality. First one, of course, you are using arrays or data structures, you are accessing the elements of the arrays one by one, as I have said just now. So, when you are accessing the elements of the array one by one, for accessing data you are exhibiting special locality. You are accessing x0, then x1, then x2, then x3 like that. Okay. Similarly, when you have iterations and loops, possibly they will be working on some regular data like arrays, or they may be carrying out some repetitive operations. So, whatever operations are there in a loop, like for example, you have a loop, several instructions, you have a loop. So, these set of instructions will be executed repeatedly. This exhibits special locality. So, when one instruction is accessed, the nearby instructions will also be accessed in the near future. Okay? This kind of property holds. There can be other reasons also. Many computer systems has an instruction for block transfer, or you may need to do block transfer for various purposes. Like for example, when you read some data from a disk, normally you do not read one byte at a time, but rather an entire block of data gets transferred from the disk into memory. Or from the network, when a packet comes, you are downloading a packet. That packet also refers to a block of data. The data contained in a packet, network packet, that will be read and will be stored in the memory. These are all some kind of block operations. So, if you think of the memory, inside the memory there is a region which typically we refer to as buffer. So, these blocks which are transferred are temporarily stored in the buffer. Suppose one block is stored here. Let us say block will contain 2 kilobytes of data. So, there will be a sequence of data that will exhibit special locality. I am storing in the first one, then second, then third, then fourth. Okay. So, this will result in special locality in accessing memory when you are doing block transfer. And lastly, this is for regular instruction execution. You know, in a typical computer system, you have a program counter that points to the next instruction to be executed. Unless there is a jump or a branch instruction, instructions are executed one by one in sequence. So, by default, instruction execution exhibits special locality. First instruction will be executed, then second, then third, then fourth, and so on. So, all these reasons, they result in special locality, this kind of property in a program. So, essentially special locality means there are some memory locations. Now, when I say memory locations, they can be either instructions or they can also be data, instructions or data. What I am saying, this set of instructions somehow they will be executing either repeatedly or one by one. So, when you are executing one instruction or accessing one data, it is likely that the next data will also be accessed, the next to next will also be accessed, like this. This is what is referred to as spatial locality. So, basically this temporal and spatial locality, what it means? It means, see, if you think of demand paging, some pages are needed in a program, you load it from memory. Because of this locality property, you can make a guess that when you are loading a page into memory, it is likely that that particular page will again be used in the near future because of this locality property. So, you would not like that a page which you brought from disk into memory, you will immediately replace it very soon, then the property of locality will get destroyed. Okay? This is what you try to do. Now, let us specifically talk about page replacement. So, this is a scenario where a page fault has taken place, but you have no free frames in memory. This is a scenario. Under this scenario, what will you do? When there is no free frames in memory, I said, when there is a page fault, of course, you will have to bring that requested page. But if the memory is full, you will have to remove one of the pages before you can bring the requested page in. So, one of the pages in memory which was present in memory need to be removed. This is the first thing, and when I say removed, we sometimes refer to this as swapped out. You move it away from memory, so that the page the process has requested, which is the incoming page, that can be loaded in memory. Now, this is the terminology which is used. The page you are removing, there may be thousands of pages in the memory, out of them one of them you are removing. That page is referred to as the victim page. Now, selection of the victim page is of course important, because you should not disturb the property of locality when you are replacing a victim page. Now, the thing I also mentioned it in the last class, that when you are selecting a victim page, what you do? So, this is your memory, let us say this is your memory, these are the pages. Out of them, one of the pages you are selecting as the victim. So, the victim page has to be removed from memory. So, when you are removing from memory, you have to check whether the page was modified or not, because I told one copy of this page is present in the disk, either in the swap area or in the normal file system. So, whenever you find that there has been some modification in that page, so we say that the page is dirty. When some modification is taking place, we say that the page has become dirty. If no modification, we say that the page is clean. If we find that the page is dirty, then during swapping out, you will have to write this page back into secondary storage, disk or whatever secondary storage. So, not only simply removing, you may have to write it also. But if the page is clean, there is no change, the copy is already there in the disk, no need to write. So, during this page removal, you may incur either one or two disk accesses. The requested page has to be brought in anyway. The page which is going out may or may not be required to be written into disk, secondary memory. Okay. So, that is what is mentioned here. If the page being removed has been modified while we are using it in memory, then while you are removing it, it has to be written back to secondary memory. Now, this selection of victim page, possibly writing it back to memory during removal, results in something called page replacement strategy. So, what is the strategy we need to follow to select the victim page and to remove it from the memory? So, generally speaking, we would like the operating system to select the victim page in such a way that there will be minimum number of page faults. Okay, this is ideally what we would like, but of course, this is wishful thinking. We really do not know what kind of memory access patterns the process will make, but at least we can try to do this. We can try to have a page replacement algorithm that will result in minimum we should not say, less number of page faults. Here we are exploiting the property of locality. What we are saying is that a page which is accessed at some point in time is likely to be again accessed in the near future. But if you find that a page was not accessed for a long time, possibly it will not be accessed in the near future also, something like this. So, the property of locality of reference you are trying to exploit in trying to select the victim page. So, you will not select one page as the victim which is being accessed very recently, that will be a bad strategy. Okay. So, some of the issues regarding page replacement strategy again. Let us talk about this. Now, as I discussed earlier, whenever there is a page fault, there is a trap or an exception to the operating system. The operating system will be handling the page fault. So, whatever needs to be done. Now, as part of this, page replacement may also need to be done. You have to find a free page frame in memory. If free page frame is not available, you have to select a victim page. If it is dirty, you may have to write back. So many things are needed, right? So, this entire page replacement business, this thing you can include as part of the page fault interrupt handler itself. Whenever there is a page fault interrupt, the interrupt handler or interrupt service routine that can contain all these routines directly. Okay? That will be easier for the operating system to handle it like this. But I told you, you need to know whether a page is dirty or clean, right? If it is dirty, then during replacement you may have to write it back. So, the point is, how do you know that a page is clean or dirty? What we do? We add one more bit to the page table. Earlier we said we had added one bit, valid invalid bit, but now we are saying we are adding one more bit, which are calling as modify bit or dirty bit. Okay. This bit will indicate whether the corresponding page was modified or not. Let us say this modified bit equal to 1 will indicate that the page is dirty, that means it was modified, and this modify bit equal to 0 will indicate that the page is clean. So, this kind of a convention you can use. Now, whenever there is an access to the page, CPU generates an address, and through logical to physical access mapping, you are accessing the page. So, immediately this modified bit of the page will be set to 1, not accessing when you are writing into the page. So, whenever there is a write into a page, that means you are modifying, the corresponding m bit in that page table will be set to 1. So, initially all the page table entries will be having their m bits equal to 0, they are clean, but whenever there is a write, the corresponding bits will be set to 1, right. So, when you find that the victim page you have selected has its m bit set to 1, you will know that it is dirty. So, it has to be written back. Okay. So, this process of page replacement, this I talked earlier also, this completes the separation between logical address space and physical address space. The size of logical and physical address space may be large, may be different. A very large virtual address space may be executed on a smaller physical memory or vice versa. Okay. This is the beauty of virtual memory. Okay. So, pictorially let us try to understand what. Let us say there are two processes, process 1 and process 2. Suppose each of these processes has 4 pages each. Process 1 has pages A, B, C and D. Let us give some names. And process 2 has the pages E, F, G and H. They correspond to page number 0123, 0123. So, each of the processes will be having their own logical address space, their own page table. And suppose this is the view of your physical memory and these pages are loaded in memory, not all of them. For example, in process 1, let us assume the pages A, C and D are loaded, but the page B is currently not loaded. So, if you look into the page table entries, you will see that for B, the valid invalid bit is marked as invalid, page is not there. Similarly, for process 2, we are assuming that the page G is not loaded. So, in the page table entry it is marked as invalid. Okay. Now, if you correlate for the page table for process 1, this one, page number 0 is located in frame number 6. So, you see frame number 6 you have page A. Page C, which is page number 2, is located in frame number 3, this one. So, in frame number 3 we have C, in frame number 2 you have D. So, like this from the page table you can know where your pages are located. Now, let us see, process 1 was executing, the program counter somehow is pointing to some memory location inside this page B. So, next time when you are trying to fetch an instruction, you are trying to access page B, and when you access the page table you find that the bit is invalid. So, this will result in a page fault interrupt. So, what the page fault handler will do? It will go to the secondary storage and it will try to locate where this page B is located in secondary memory. So, it will be trying to bring that page back into memory, but when it is trying to bring it into memory, it may find that the memory is already full. So, it will have to select one of the pages for removal. This is the idea behind page replacement victim page selection. Now, which of these 6 pages we will be selecting, that depends on some policy. So, those policies we shall be discussing subsequently. Okay? This is the basic idea. Now, the stepwise what happens is that once you select a victim page, suppose you select a victim page, let us say in physical memory you have select one page, any one page which you want to remove. First step is you swap out victim page. Swap out may require write operation. If the victim page is dirty, then you may have to write it back into secondary memory. But if it is not dirty, you simply throw it away, do not do anything, because the copy is already there in the secondary storage. Then whatever is the requested page, you bring it from the memory. But before that, as soon as you swap it out, mark the corresponding page as invalid. This was V, so this V will immediately become invalid. That page is no longer there. Next, you bring the requested page, that is step 3, swap in, swap the desired page into memory. So, you have already made space in frame number F. So, in same frame number you bring this new page. After bringing this new page, you will have to adjust the corresponding entry in the table, reset page table for new page. So, whatever is the page number, you create that entry in the page number, you store the frame number there and mark it as valid. Maybe it will be some other entry in the page, maybe here, maybe it will be here, you make it F and V, depending on which page number it is of the logical address space, right. This is how the thing works. Now I have said that we need to have a page replacement algorithm, which desirably should exploit the property of locality of reference, so that the recently accessed pages should remain in memory. So, for a page replacement algorithm, what are broadly the steps? Diagrammatically I have already shown, here we are showing the steps. First step, find which page has to be brought into memory. See, the process is trying to access a page, a memory location corresponding to a page. The page is not there in memory, in page table it is marked as invalid, there is a page fault. So, now the requested page has to be brought from secondary storage. So, first you find out the address of the desired page on secondary storage, swap area or file system area, wherever it is. First find out from where you have to bring it, then try to find a free page frame in memory. Free frame list, the data structure is maintained by the operating system. So, the operating system will be consulting that free frame list and try to find out whether a free frame exists or not. If you find that a free frame is there, it is found, simply use it, block it, I want to use it, remove it from the free frame list. But if there is no free frame, here the page replacement issue is coming into the picture. So, you will have to first select one of the pages to remove. So, you will have to select the victim page for removal. So, as I said, there may be various algorithms and policies as to how you select the victim page, and once you select the victim page, you also check whether the dirty bit is set or not. If you see that dirty or the modified bit is set to 1, which means that there was a write operation on that page, you will have to write it back into secondary memory when you are swapping it out. So, after you have done that, you have created space for the new page which is to be swapped in. So, now you copy the desired frame from secondary memory to the free frame you have created, either free frame was existing or you have taken out a victim page. And once you have done that, you will have to update both the page table and if required also the free frame list. So, after everything is done, everything is in place, you will have to go back to the program which resulted in the page fault and restart the instruction that caused the page fault. So, one thing you see here is that for every page fault, there can be maximum of 2 page transfers. Page transfer means I am saying between memory and disk. So, there can be maximum 2. There will be one mandatory read because you are reading a page, but if a page is dirty, you may also have to write. So, this is the point to note, that in the worst case you may have for every page fault 2 disk accesses, one for a page read, one for a page write. Okay. Now, the second thing is that we will see that we can have several different page replacement algorithms. Suppose I have 2, 3, 4 algorithms, but I am asking a question now, which of these 4 is good? So, which one should I use? Typically, we evaluate these algorithms through some kind of simulation. So, how we do the simulation? We create something called a page reference string or simply reference string. It means, you see, you think of a process. You think of a process Pi which is running. When a process Pi is running, what the CPU will do? The CPU will be executing these instructions one by one in whatever order it is, there is branch, jump, whatever. So, CPU will be generating a sequence of memory addresses, right, during the execution, and these sequence of memory addresses translate to a sequence of pages that are being referenced. So, that sequence of pages that are being referenced is basically the reference string of the program. So, it is always good to have a realistic reference string. There are some programs using which you can generate the reference string of a real program, But in our examples, we shall assume some example reference string, some example page references, with respect to which we shall try to find out which algorithm gives how many page faults, which is good, which is not so good, right. So, with respect to this reference string, which is nothing but some sequence of memory references, we try to compute the number of page faults. But when you are calculating the number of page faults, we also have to assume some model of the memory, like how many frames it can store. Okay? So, we shall see the examples when you look at, we shall see how we do that. And as I said, the reference string essentially contains just a sequence of memory references which you represent as a sequence of the logical page numbers, because we are interested in the page numbers only, how the page numbers are accessed, whether the pages are in memory or not. If they are not in memory, there will be a page fault, otherwise no page fault. And as I said, this experiment will be run assuming certain number of page frames in memory, and the actual number of page faults that will occur, this will very much depend on the number of available page frames. So, you can have 3 page frame, 4 page frame, 10, 100, 1000, whatever. You assume that there are so many page frames with respect to which you simulate on the reference string and try to find out how many page faults will occur. Okay. But of course, as I said, if a page is referred and you find that the page is already in memory, there will be no page fault. Okay. But if it is not in memory, then there will be a page fault. Okay. Now, we shall be looking at a number of different page replacement algorithms. So, let me talk about them very briefly today. In the next lecture, we shall be going into some detail on this. First one is a very simple algorithm, first in, first out. It does not consider or does not take any special care about preserving locality of reference. First in, first out means the page which was brought into the memory first will be the first one to be swapped out. Simple. But the problem is, the first page which is brought in may also be the page which is most frequently being used. So, you are removing one of the most frequently used pages from the memory. So, immediately it will be accessed again there will be a page fault, you will have to bring it back. Okay. And the second one is, this is a theoretical algorithm, it cannot be implemented in practice. This is called optimal algorithm. What we are saying is that we select the victim page as follows: the page which will not be accessed in the near future, the page that will be accessed farthest away in the future, select that one for removal. But for that you will have to go to an astrologer, you will have to see the future. That is why I said optimal algorithm cannot be implemented. It is a theoretical kind of a study. You replace an algorithm that will be used farthest away in the future. It will not be accessed in the near future. Then you have an algorithm called least recently used. Least recently used means you cannot see the future, but you can predict the future. Least recently used means you are predicting the future based on the immediate past. What we are saying, what happened in the future, in the past, same pattern is likely to occur in the future as well. So, the page which was accessed least recently will be the page that will again be used in the near future. Okay. So, you can say LRU is an approximation of the optimal algorithm, And similarly, this LRU, if we try to implement as it is, there will be a lot of overheads coming in. So, there are some approximations also. We shall be looking at some of the simple ways in which you can implement LRU or something similar to LRU. So, these are the different algorithms that we shall be discussing, but one thing we said that all these algorithms we shall be evaluating with respect to a reference string. Reference string I am repeating. There is a CPU which is executing the instructions of a process. CPU is generating the memory addresses. Let us assume that the memory addresses CPU is generating are A1, A2, A3, A4 and so on. Sequence of memory addresses that are being generated. Now, each memory address, let us consider memory address AI will consist of two parts, as I have said earlier in paging. One part will be the page number, let us call it PI, other part is the offset, let us call it DI. Now, here we are more interested about page replacement, that is why you are more interested about the page numbers that are being accessed. So, instead of this addresses A1, A2, A3, A4, we only consider the sequence of page numbers that are being accessed P1, P2, P3, P4, and this will be your reference string. And the kind of simulation that I told about, what do we do there? Suppose this is your algorithm, this is your page replacement algorithm. So, what you do? You feed this reference string, which is a sequence of page number, as input to this algorithm. You give this as input, reference string, and the simulation that you are doing will give you some statistics, how many page faults are occurring. So, if you evaluate two different algorithms, you see that the number of page faults are, let us say N1 and N2, whichever algorithm is giving less number of page faults, you can say that algorithm is better, at least for this process. So, in this way you can evaluate the different page replacement strategies and algorithms and try to find out which one is better. Now, we shall be looking into some detail about all these algorithms in our next lecture. So, there is another issue that I want to talk here, that I said that when you do the simulation, we do the simulation with respect to a certain number of frames in memory. So, that simulator, if I want to refine it slightly, the simulator will take as input, one input will be the reference string, the other input will be number of page frames, and this, as I said, this will give you the number of page faults. The number of page faults will obviously depend on how many frames are there in the memory. Now, what your intuition says that as we increase the number of available page frames, the number of page faults should decrease, right? This is what normally we expect. Normally, the number of page faults will decrease when the number of available page frame is increased. More number of page frames, you can hold more number of pages in memory. So, the chance of page fault occurring should be less, right. But for some algorithms, you will see there can be a scenario where the reverse occurs. As you increase the number of page frames in memory, the page fault can also increase. This is something which is called Beladi's anomaly, which was observed by a researcher called Beladi. It is known as Beladi's anomaly, and the reason for Beladi's anomaly we shall also be talking about in the next lecture. Now, normally this graph shows what is our expected behavior, that as you increase the number of frames in memory, the number of page faults should decrease steadily. Of course, beyond a point it may not increase any further, because the process does not require any more frames. You have given all the frames it requires. But in reality, as I said, due to Beladi's anomaly, for some algorithm you may see a behavior like this. It was decreasing, but suddenly it is increasing, again decreasing. Some behavior like this can also happen. Okay. So, this we shall be seeing in our next discussion classes. So, with this we come to the end of this lecture. So, if you summarize here, we were basically talking about page replacement and page replacement policy here. Victim page, how do you select the victim page? And most importantly, I want to repeat, we are very strongly relying on the property of locality of reference. Whatever algorithm we propose, whatever strategy we use, we assume at the back of our mind that we want to comply with the property of locality of reference, because that is a property of program behavior that is seen for most of the programs, and that is our assumption, that the program that we are running, that will also be exhibiting very good locality. So, if we can keep all the pages in the vicinity of the page being accessed right now in memory, the chance of page faults occurring will be less. That is the general understanding. So, with this understanding we shall see in the next class how we can design our page replacement algorithm strategies, and we shall also evaluate, of course, with respect to how many page faults they result in. Okay. So, with this we come to the end of this lecture. Thank you.